Hey everybody, this is Mr. Brooks for our final lesson in Chapter 11. It's dealing with applications of Taylor polynomials. So just in the last section, we introduced what Taylor series and Taylor and Maclaurin series were by their definition. So what we're going to do now is look at some ways that we could use Taylor polynomials, which is just a partial sum of a Taylor series. So that's why if you look at the notation that you'll see these i's pop up, and that's just because we're saying that we're going to take a finite number of terms for this. And so what we're going to see is there's some big questions is like why do we need this? And we kind of answered that in the last lecture, which is for things that we don't normally know how to integrate, say e to the x squared or sine of x squared, things like that. We don't have the normal means to evaluate those, like if we were to take the integral. And so this is where Taylor series and Taylor polynomials is going to come into play, because we can then find a power series representation of those specific functions. And so what we're dealing with is a polynomial, and we can integrate those all day long. And so because we just do it term by term. And that is the big benefit of that. But the question comes in is, well, what's the accuracy level that we are going to achieve with that? And so those are some of the questions that we're going to be asking and answering in this lecture. So first of all, again, a Taylor polynomial is of the form t sub n of x is equal to the summation as I goes from 0 to n of s of I, this is the ith derivative, okay, and then a again is our center in this case. So we're seeing this is our c sub n. So recall real quickly from just normal power series, a power series is of the form c sub n of x minus a to the n. And so with Taylor series, we actually found a representation of this in terms of x. So that's where that's coming from, because we wanted to relate it back to the function. And that's where we got this nice, well, you could say clean formula for that. And so if we looked at the terms of this, this would just be f of a plus f prime of a divided by 1 factorial times x minus a plus f double prime of a over 2 factorial x minus a, the quantity squared, and so forth, up to the nth term. Okay, so one important note that we want to make here is that the first, and we saw this in the previous class, so this is just reiterating it, the first degree Taylor polynomial is exactly the same as the linearization of f at a. And again, we use linearization for things that we want to quickly approximate, and this is something that we learned in Calculus 1, because since we're talking about linearization, we're dealing with a line, and we can just plug in a simple value of x, and we can quickly get an approximation. Now, again, with linearization, the further that you get away from your center or from that point, the worse that approximation is going to become. And so that's something we are actually going to address in this situation as well. So for notation, t sub 1 of x is equal to f of a plus f prime of a times x minus a, which is equal to the linearization at that point. Okay, so again, linearization is a great approximation tool for really complicated functions. We can get a quick, easy value to approximate near that point. And so this makes calculations a lot quicker, and especially if you're not looking for a high level of accuracy, then we can use this for several calculations. All right, so one thing to get back into the swing of things is we talked about these graphs, and so I wanted, instead of seeing these singular graphs, I wanted to double up. So I got these off of Desmos, and this is how you could see how quickly these are forming. So for example, if we looked at e to the x, so this is our function that we're dealing with, and we found out that e to the x has a power series representation of x to the n over n factorial. All right, and we found out its radius of convergence was actually equal to infinity in that case. So what I've done here is I have graphed the Taylor polynomial starting with t is equal to 1. So this is 1 plus x here, and in the red here is our e to the x. So notice that around our center of 0, as we slowly go away from it, notice that the difference between these two functions becomes more and more and more. And so we're pretty accurate around this, and actually really accurate around x is equal to 0, but even if we slightly pull away from it, even at 1/2, we start seeing a big discrepancy between the values. All right, so let's bump it up. Well, if we look at t sub 2 of x, so if we look at the second degree Taylor polynomial, x squared over 2, and e to the x, notice that we're fitting that curve a lot better until this point, and then it starts separating out between the two. All right, well, let's bump up the accuracy a little bit more. So here I have just a third degree. So this is just using the first 4 terms of this Taylor series, and look how close it is up to -1 and up to 1. So notice that we're really fitting that curve pretty well in there. All right, and the last one I just want to show you, if we used a 5th degree Taylor polynomial, and here I had to use a dotted line. The black dotted line here represents a 5th degree Taylor polynomial. Now again, these terms are a little bit daunting, especially when you get into the factorials, so I didn't want to go too far out. But still, notice how close, or it's almost exactly on that line for a very large interval. In fact, we have seen, since we said that it does have a power series representation, the further we expand out this Taylor polynomial, the more accurate, or the more it becomes e to the x, for that matter. So again, each t sub n is a better and better approximation for values near the center. Again, that's its center. So let's look at some values here just to demonstrate what's going on. So I'm going to look at approximations for when our center is near 0, 2, using these Taylor values, or Taylor polynomials centered at 0, and then seeing what happens the further we go out. So let's just go out 3 units away from the center. So here I'm very close to the center with this first value, and then further out with the second value. All right, and then this is going to be our t sub n of x here. So if I look at the square, so a Taylor polynomial degree 2, degree 4, degree 6, and we'll do degree 8 with this as well. So let's check those values. Again, our center is at a is equal to 0 for both of these, and so we should expect to see a very close value when we get to when we're closer to 0, and then we should start seeing a bigger discrepancy as we go further away. and then I'm going to compare it to e to the x down here at the bottom. All right, so if we plug in 0.02 in our second degree Taylor polynomial that we just found, or Maclaurin series actually, we get 1.22. If we plug it into the fourth degree Taylor polynomial, 1.2214, sixth degree, we get 1.226403. So notice how it's slowing down, but it's still increasing, but we're getting closer and closer approximations here. And 1.221403. Oh, so this was supposed to be a 1 here. So notice that it's kind of slowed down. And in fact, if we go out only 6 decimal places, we find out that we are very high level of accuracy when it comes to that, even using just a 6th degree Taylor polynomial. However, since we're 3 units away, let's see what happens. I get 8.5, and then notice a big jump here, 16.375. And then I get 19.4125, and then 20.009152. And then if we compare that to our exponential, we get 20.085537. So notice that there is a huge discrepancy between these, and that should make sense because if we go back to our graph here of we're coming out to here with 3. Notice the distance here is almost the value of 1. Well, it's about 0.75 if we looked at the difference between the Taylor polynomial evaluated at t is equal to x is equal to 1 versus e to the x. So notice there is going to be a bigger and bigger discrepancy as we go. But as we match it, as we get a larger number of terms for the Taylor polynomial, notice that that distance between the two starts decreasing. And in fact, if we used a 10th degree Taylor polynomial, we'd actually be pretty close because if we did the 10th degree Taylor polynomial evaluated at 3, we'd get approximately 20.0796 and change, which that's pretty close to it. Now again, we have to go 10 degrees out to get there, whereas with the closer to the center we have less error that's occurring. So again, that's the big thing. So if we wanted to have a better approximation, we move the center. And so that's what linearization also did. If we want a better approximation near a certain point, then we find the linearization at that point. Same thing with Taylor series and Taylor polynomials. If we want better approximations, move the center. All right. So then we can ask ourselves, well, how approximate is it? So again, when using a Taylor polynomial to approximate f, we must ask the following 2 questions. 1, how good of an approximation is it? And 2, how large of a degree do we need in order to have the desired accuracy? So are we going to have something accurate, and how many terms are we going to have to get there to get to that accuracy level that we want? Well, there's 3 ways that we can determine this particular question, or answer this particular question. So the first one is like what we just saw up here. I can use a graphing calculator and come up with the approximation that I need based upon just different iterations of the Taylor polynomial. All right. So first group is a graphing calculator or graphing device to approximate. But since we're in calculus, we know we're going to be doing something different than that because that feels like we're cheating. So the other thing is well, we have seen alternating series pop up. Well, the bad thing is we have to make sure we have to have an alternating series before. But one of the ways, again, is the alternating series estimation theorem. Again, I'm going to reiterate this only for alternating series. Okay. The next one, in all cases, so this is good. So this is so like the quadratic equations has the quadratic formula to answer any zero question that we have for it. This question here, how accurate can we get, or what is the accuracy level, we actually have something that is the catch-all. And so in all cases, we can use Taylor's inequality. All right. So remember, if the absolute value of the nth plus 1 derivative, again, this is talking about the size of it. So what's the largest value it can be? So we're going to put an upper bound on it of m. Then the remainder of the series is less than or equal to big M over n plus 1 factorial x minus a to the n plus 1. Now we use Taylor's inequality to prove that the exponential and sine both had a power series representation. In fact, we proved it for all values of x. Here we're going to use it to say, well, how accurate are we? So we're going to look, and we can actually calculate the largest error that we would have on a particular interval, which is really cool. So let's apply that to this guy. Approximate f of x is equal to the cube root by a Taylor polynomial of degree 2, centered at x is equal to 8. How accurate is this approximation when x is on the interval from 7 to 9? All right. So first thing that we need to do is we need to develop that Taylor polynomial. This is probably the easiest step of it all. So here's our solution. So f of x is equal to x to the 1/3 power. F prime of x is equal to 1/3 x to the negative 2/3 power. F double prime of x is equal to negative 2/9 x to the negative 5/3 power. And I'm actually going to go one step further. Yes, I could stop here, but if you look at Taylor's inequality, I'm going to have the nth plus 1 derivative. So if I'm looking for a degree 2, might as well go ahead, and since we're on a roll, find out what the third derivative is, because we're going to need that later on. All right, and so we're going to get 10/27 x to the negative 7/3. All right, and now we need to evaluate all of these at the center. Well, except for x is our third derivative. So f of 8 is equal to 2. F prime of 8 is equal to 1/12. And f double prime of 8 is equal to 144. All right, so our Taylor polynomial of degree 2 is equal to f of 8. And again, I'm generalizing this so that way you can see where these values are coming from. So then that way it's not like, okay, he just put these down, now I can't figure out where we're going. All right, so notice now the largest power of x is going to be raised to the second power. So this is my Taylor polynomial of degree 2. So we're saying this is equal to 2 plus 1/12 x minus 8 plus, and since we had left my negative off, negative here, negative 1/44 minus 1 over 1/44 divided by 2, so 288 x minus 8, the quantity squared. So make sure when you're doing Taylor polynomials that you make sure to divide by the appropriate value under there. Okay, so that's a pitfall that I've seen from other tests before in the past, so I just want to reiterate that when you're going through this, to make sure that you divide by that. If we're going out to a second degree, you divide by 2 factorial for that last term. If we go out to a third degree, you're going to go divide by 3 factorial and so forth. So make sure that you divide that. So we're saying this is going to be approximately equal to the cube root of x. All right. So this is part of our solution. We found Taylor Polynomial degree 2. So it looks like it's an alternating series, except for one thing here. Because again, we could use alternating series estimation theorem in order to talk about this, and we know where these guys converges. But this is the issue. The Taylor series is not alternating when x is less than 8. Because if we look at this, if the value of x is less than 8, then this becomes negative. This maintains as a negative. So we'd get negative values all the way through except for the first term. So every value above x is equal to 8 is now an alternating series. But since we're in that interval from 7 to 9, we can't use alternating estimation theorem. If we were outside of it, we could, but not the case. All right. Thus, we cannot use the alternating series estimation theorem, which you probably figured that I was not going to use this because we need to use Taylor's inequality. We know Taylor's inequality is the catch-all for it, so that's why we're going to do that. So let's look at the things that we have. We know n is equal to 2, a is equal to 8, and we're on the interval from 7 is less than x, which is less than 9. All right. And again, here's Taylor's polynomial, or sorry, Taylor's inequality. And I'm going to write this out, and then below it, we're going to plug in the values as we go. All right. So here's our first part. So let's plug in the values. Well, we said if we're dealing with a second degree Taylor polynomial, so n is equal to 2. We're still going to need to find what big M is, so we're going to get there in a second. So since n is 2, we're going to get 3 factorial here on the bottom, and then x minus 8 to the third power. Again, n is equal to 2 in this case. All right. So this is what we want. This is what we're shooting for. We need to figure out what big M is, and there's a couple other things that we need. All right. The if part, which we should have started first. So the beginning of Taylor's inequality is if f of n plus 1 derivative of x is less than or equal to big M on some interval that we have. All right. Well, let's think about this. There's a couple things that we can talk about. The nth plus 1 derivative, so for us, we're saying the third derivative is less than or equal to big M. Well, we just said the third derivative is 10/27 x to the negative 7/3. Okay? And we're on the interval from 7 is less than or equal to x, which is less than or equal to 9. So let's see if we can rewrite this. Well, we know x is equal to, or sorry, a is equal to 8. So if I subtract by 8 from each of these terms, I get negative 1 is less than or equal to x minus 8, which is less than or equal to 1. Using properties of absolute values, this is saying absolute value of x is less than or equal to 1. Okay? So notice now we match what we're going to do here. We're going to use this here in just a second as well. All right? So let's talk about this less than or equal to big M. So I need to cap this off. We can't allow the derivative to be larger than this number. We can have it equal to, but we can't have it larger. Well, think about this. We have 10 divided by 27 times x to the 7/3, meaning our denominator, or our variable is in the denominator. So on the interval from 7 is less than or equal to x is less than or equal to 9, the largest f double prime of x is is at x is equal to 7. Again, we're looking for a cap on this particular interval. Okay, so when I plug in 7, that is going to be less than if I plugged in the value 9. So here I'm trying to maximize what m is. So by doing that, I have to use the smallest value of x because the larger the denominator, the smaller the number. So that means f double prime of x is less than or equal to 10 divided by 27 times 1 over 7 to the 7/3 power, which is approximately equal to 0.00206. Oh, I messed up. Let's go back for a second because we need to fix something. This is supposed to be to the 8th power. I subtracted by 2 instead of by 3 when I dealt with this. So I need to fix some things. So we'll make a note of that. So I'm going back through here fixing my mistake. My apologies. This is supposed to be 8 here. So again, make sure that's to the negative 8/3 power for the third derivative. All right. So now your calculations should be true. So 8/3 there. All right. Again, this is approximately 0.00206. So this is the largest that the third derivative will be on the interval from 7 to 9. So this is our big M. All right. Therefore, we can say big M is equal to 0.00206, and absolute value of x minus 8 we just found out is less than or equal to 1. Again, coming from our interval, so we're trying to match this x minus a is less than or equal to d, so the distance from the center. And so on this interval, if I subtracted by 8 all the way through on this inequality, then I get the absolute value of x minus 8 is less than or equal to 1. That's where this is coming from. Again, work to the side to show where this is coming. 7 is less than or equal to x, which is less than or equal to 8. I subtract all the way through by the center. Negative 1 is less than or equal to x minus 8, which is less than or equal to 1. Property of absolute value. And that's where that's coming from, which is good because think about what we need. We need this statement here. X minus 8 is less than or equal, or is this absolute value of x minus 8. All right. So, thus, Taylor's inequality gives us R sub 2 of x is less than or equal to 0.00206, so that's our big M, divided by 3 factorial, times x minus 8 we just said is less than or equal to 1. So I'm going to maximize this and say that that is the value 1 to the third power, which is equal to 0.003433. This is how accurate this is going to be. So thus, if x is between 7 and 9, the approximation is accurate to within 0.0003433. So that's a pretty good accuracy. So we're less than a thousandth away from it. So that's very stinking close if we're dealing with this. So just using a second degree Taylor polynomial on an interval from 7 to 9, we have a pretty high accuracy rate for that. And in fact, we could say, well, how can we make it more accurate? Well, the more terms that we make it, that we add to it, the higher level that we're going to get. So let's do another one of these now that we get the swing of things. Use the natural log of 1 plus x to estimate the natural log of 1.1 to within 0.0001. How many terms will you need? So think about this. Does anybody know how to calculate the natural log, besides using a calculator, by hand? If you do, that's great. You're going to surpass my knowledge. However, more than likely, this is something that we can't do. But if we have a polynomial, we can use that. So there's a couple things that we need here. We need the Taylor series for this guy. Well, luckily, this is one of the known ones that we have. All right. So the natural log of 1 plus x we have found before and goes from 1 to infinity of -1 to the n minus 1 x to the n over n. And here our interval of interest is between, our radius of convergence is 1. All right. So this means our center, if we look at the formula, x to the n, that's going to tell us the center is at a is equal to 0. All right. So since we're within 1 of this, say 0.1, so notice here that our value is not going to be that bad. All right. So when we do this, we say the natural log of 1.1. Well, we want to match this. Well, this is the natural log of 1 plus 0.1, which means this is our x value. So this is equal to the series as n goes from 1 to infinity of -1 to the n minus 1, 0.1 to the n over n. Well, if we look at this, this is an alternating series. Meaning we can use the alternating series estimation theorem. Why are we allowed to go straight into that? Well, think about it. We know that this converges on the interval from -1 to 1. And our value of x is inside of that interval. Therefore, this is a convergent series. So, and you can verify this using the alternating series estimation theorem. Sorry, the alternating series test. All right. Well, A set says if we have a convergent series, then the remainder of that series is equal to s minus s of n, which is less than or equal to the nth plus 1 term. Okay. So we want to be within 0.0001 accuracy level. Okay. So if we look at this, so there's a couple ways that you could do. You could try the algebraic technique. Since you're dealing with that 0.1 to the n, I would suggest looking at a term by term investigation is the best way to do this one. And in fact, we don't have to go that far out. So our first value we're going to get is 1, or 0.1, minus 0.005 plus 0.00333, minus 0.000025, and just to have another one for kicks, 0.000002, and so on. Well, again, I want to be within 0.00001 of this value. So I'm going to say this is A1, A2, A3, A4, A5. Well, this one has an issue with our error that we want. We want to be within 0.0001. This one is not close enough. This one is just outside of it. That 3 is messing us up. So that fourth term, however, notice we have a 0 here, and there's not going to be a round off issue with 0.000025. So this is within our accuracy level. So if we looked at this, the absolute value of a sub 4, which is equal to 0.1 to the fourth over 4, is approximately equal to 0.000025, which is less than our error. Now again, this is our nth plus 1 term, which means we just need the first 3 terms to get there. Okay, again, because we're saying the nth plus 1 term, that's our error that we're wanting. Okay, so we need the first 3 terms, and I'm going to put non-zero here in case those pop up. Of this Maclaurin series. For the desired accuracy. And 0.1 minus 0.005 plus 0.000333 is equal to 0.95333. And if we look at the natural log of 1.1, this is equal to 0.09531,018. So those are extremely close to each other. And in fact, notice the first 4 terms are first 4 digits are exactly the same. All right. So this is how we can use Taylor polynomials as approximations and also find out how accurate we are. So that's the cool thing about this section, is we can use a Taylor polynomial to approximate anything we want, and then also we can find out how accurate is it on a particular interval, or how many terms we are going to need in order to be within a certain accuracy. So that's all we're going to do for the day, and that ends section 1111. There's really good examples in the book, and there's practice problems that you can get in there. And so also look at the notes on Canvas, because I do have a good write-up of a Taylor polynomial problem from 1111 that is just by itself. So it's I think a single page that you can have access to. Y'all have a wonderful day. It's been a great semester, and that's it. Have a good day.